Follow the curve sketching recipe to graph. The first thing we're going to do is figure out what is the domain. This is a polynomial function. A polynomial is continuous from negative infinity to infinity. So the domain here is negative infinity to infinity. All real numbers are part of the domain. The x-intercepts occur when y is equal to 0. To solve for x-intercepts, we make f of x equal to 0 and solve for x. These x values, or the zeros, would be 0, 1, and -2, which has a multiplicity of 2. That does not show up graphically, but it's important to recognize so that you know you have all of your zeros. This function should have 4 zeros, and it does, because -2 occurs twice. They've asked for the x-intercepts rather than the zeros, so I need to write them as xy points, 0, 0, 1, 0, and -2, 0. The y-intercept is what we get out of the function when we plug in 0 for x. So solving this equation, and that would be 0. Well, that makes sense, because if 0, 0 was one of our x-intercepts, then 0, 0 is the y-intercept. We should only have one y-intercept, otherwise we would not be graphing a function. EB stands for your end behavior. Now, end behavior is often talking about any sort of horizontal asymptotes. In this case, we have a polynomial, so we don't have any asymptotes, but we have the leading coefficient test to give us the end behavior of any polynomial function based on its degree and its leading coefficient. So if we were to expand f of x, the first term would be x to the power of 4, and the coefficient for that is just 1 if I were to multiply these out. I only care about the leading coefficient, so I don't need to expand the rest of the function. If the degree is even, then your end behavior is the same. Either both sides will approach positive infinity, or both sides will approach negative infinity. The leading coefficient is positive, so we will be approaching positive infinity. As x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x is still approaching positive infinity. The degree is even, the end behavior is the same. Okay, I got all this information. How does that translate into graphing? Well, my first step is to put any restrictions to the domain. If there are any vertical asymptotes, I want to draw those. There aren't in this case, so then I go to intercepts. Let's plot the intercepts. 0, 0, 1, 0, and -2, 0. I also know the end behavior, that to the left of -2, I will be approaching positive infinity, and to the right of +1, this intercept, I will be approaching positive infinity. That's really helpful as well. So it looks like I just need to figure out what's happening in between each of the x-intercepts. So what I decided to do was plug in a couple of numbers. I plugged in 1/2, and I also plugged in -1 to get a point in between and then to fill out my graph. Go ahead and evaluate f of -1 and f of 1/2. And for -1, the output is 2, so we'll go ahead and graph that. At x equals 1/2, the output is -25/16, which is about -1.5. Through this point, through the origin, and there we go. There is my beautiful curved sketch for this quartic function. For this example, this crazy rational function here, I'm going to start off with the domain. any discontinuities in the domain for a rational function will show up in the denominator. Zeros of the denominator are discontinuities in the domain. So, as a note to myself, x cannot be whatever makes this 0, which is 0, whatever makes this group 0, which is 1, and whatever makes this group 0, which is 3. Those are the three things that x cannot equal. They will either be asymptotes or wholes, both of which are non-inclusive. So I will use entirely parentheses to do the domain. Negative infinity up to 0, 0 to 1, 1 to 3, 3 to infinity. This is my reduced version of g of x. So if I were to reduce common factors between the numerator and the denominator, after I have reduced the function, our vertical asymptotes will be the zeros of the reduced denominator. So anything that makes the reduced denominator 0, that will be a vertical asymptote. I see that this would give me x equals 0 as a vertical asymptote. And is this an odd or an even vertical asymptote? This is an odd vertical asymptote because the degree of it is 1, which is an odd number. Then we have another vertical asymptote, which is at x equals 3. This vertical asymptote is actually even because x minus 3 is to the power of 2. So we have an even vertical asymptote and an odd vertical asymptote. Even and odd is going to help us understand the behavior on either side of the vertical asymptote. So that's really helpful information. In order to find wholes, we look at the zeros of whatever reduces to 1. So you may have noticed that x over x squared reduced to 1 over x, but x was still in the denominator, which made x equals 0 a vertical asymptote. So even though it was reduced out, it cannot be both a whole and a vertical asymptote. If it remains in the reduced version, then it is a vertical asymptote. Vertical asymptote trumps whole. Was there anything we were able to reduce that did not remain in the denominator? Yes, x minus 1 quantity squared over x minus 1 reduced to x minus 1 in the numerator. And so we had an x minus 1 reduced to 1. Well, what is the 0 of x minus 1? That would be 1. X equals 1 would make that 0. So we're going to actually have a whole at x equals 1. To find the y value of a whole, and it's not actually its value, right, because it's a whole there, but to figure out where to put your whole, you can use the limit as x approaches 1, and you'll want to use the reduced function, otherwise direct substitution will provide you with an undefined result. So we'll use our reduced function, and direct substitution actually works at this point. 1 minus 1 in the numerator would give you 0, so the entire thing results in a 0. The placement of your whole is at 1, 0. Okay, let's take a look at our x-intercepts. X-intercepts are zeros of the function. And if you have a rational function, then as long as the denominator is not equal to 0, then we don't care what it is. We want to know what makes the numerator equal to 0 because that's what makes the entire ratio equal to 0. So I will look at the zeros of the numerator. Again, I want to look at the reduced form because I don't want to accidentally say that a whole might also be a 0 because that would be impossible. So the x values that make the reduced numerator equal to 0 are 1 and negative 3. If you remember, x equals 1 produced a whole, so it cannot also be an intercept. If there's a whole there, then the y value is undefined, but if it's an intercept, the y value is 0. So I only have one x-intercept at x equals negative 3. So my x-intercept is negative 3, 0. The y-intercept is what you get when you plug in 0 for x. But if I go back to the restrictions, the discontinuities in my domain, turns out 0 is actually a vertical asymptote. So there is no y-intercept. There is nothing crossing that y-axis. End behavior is dependent on the degree of the numerator and the degree of the denominator. So I want to expand the numerator and the denominator to check the end behavior. I notice the degree of the numerator is greater than the degree of the denominator, which means I do not have a horizontal asymptote, but I do have a slant asymptote, and that will make my, if I find the slant asymptote, I won't need to plug in as many points in order to sketch the rest of the curve. So that's what we're going to figure out. How do you find a slant asymptote? We're actually going to take this numerator here and divide its denominator. Remember polynomial long division? We're going to divide, and the result, not talking about the remainder, but the result that does divide evenly, will be the equation of the slant asymptote. Go ahead and pause the video and then press play when you're ready to check your work. Here's the result for the long division, and it looks like our slant asymptote will be at y equals x plus 14. So to find the end behavior, I know that it's either going to head toward infinity or negative infinity because I have no horizontal asymptote. So in order to find the end behavior, I'm going to evaluate the limit as x approaches infinity. Now, remember that we really only care about the term of highest degree in the numerator and the term of highest degree in the denominator when we are evaluating limits at infinity. This would reduce to be x. The limit of x as x approaches infinity would simply be infinity. The other way, the limit as x approaches negative infinity of this, which reduces to be x, is simply negative infinity. Start with the vertical asymptotes. I like to remind myself if the asymptote is odd or even. This one is odd, and this one is even. Next, I want to graph the hole and the x-intercept. I'm also going to graph the slant asymptote, which is y equals x plus 14, not y equals 14. The x-intercept of this would be if y is equal to 0, so solve for x, and that would be negative 14. So your x-intercept is actually negative 14 for that slant asymptote. The slant asymptote, it is only telling us where the end behavior is headed. Same with a horizontal asymptote. You can cross a horizontal asymptote in between those vertical asymptotes. Sometimes that happens. So the first thing I'm going to do is I want to know what is happening as x approaches 0 from the left. So I want to find the limit of g of x as x approaches 0 from the left. So what I'm going to do is plug in negative 0.1 and evaluate that. So I plugged it into the reduced form, which is the same as plugging it into the pre-reduced form, and I would get 27.9 approximately. So that is headed toward positive infinity. That is much greater than 0, so it looks like we head toward positive infinity as we approach negative 1, as we approach 0 from the left. So let's go ahead and draw that. From the x-intercept of negative 3, I'm going to approach this asymptote and head toward positive infinity. Now I actually know what happens to the left of this. It follows our slant asymptote. Okay, so what is happening in between our vertical asymptotes? Well, I know that the behavior around x equals 0, since it's an odd vertical asymptote, the behavior is opposite on either side. So if the behavior as we move towards 0 from the left is approaching positive infinity, then the behavior as we approach 0 from the right will be approaching negative infinity. As we approach 3 from the left, are we going toward positive infinity or negative infinity? I want to just make sure by finding the limit as x approaches 3 from the left this time. So I'm going to plug in 2.9. Go ahead and plug in 2.9 and see what you get. That looks like it's headed toward, yeah, positive infinity. That's a pretty big number. So this one is headed toward positive infinity. And then because x equals 3 is an even asymptote, I know the behavior is the same on this side as well. This one should head toward infinity. And the rest of this branch will follow our slant asymptote for its end behavior. Just another way of writing it is absolute value x, because the square root of x squared is absolute value x. Restrictions for domain include the denominator cannot equal 0 and under a square root cannot equal a negative. Here we have under the square root is always being squared. So that is not relevant to us in this case. It's always going to be a positive. But it cannot be 0. Not because we can't square root 0, but because we can't divide by 0. So everything but 0 should be included. And it's not inclusive with 0 because 0 is an asymptote. All right, what makes the denominator 0? 0 does, and that is why it is our vertical asymptote. What kind of vertical asymptote is it? It's an even vertical asymptote. Good to know. So the behavior on either side will be the same. What are my wholes? If there's anything that reduces to 1, the 0 of those factors is your whole. But we have nothing that reduces in this function, so we have no wholes. X-intercepts, when you have a rational function, x-intercepts are zeros of the numerator, as long as they don't also make the denominator 0. So what would make our numerator equal to 0? -1. And if it says x-intercept, I want you to write it as a point, not as an x equals. Y-intercept, if we have a vertical asymptote at x equals 0, that is literally the entire y-axis. So we don't have any y-intercepts either. And what about that end behavior? To determine the end behavior, I'm really trying to find the limit as x approaches infinity and the limit as x approaches negative infinity. So I'm going to use our rewritten form, x plus 1 over absolute value x. And then remember, I only care about terms of highest degree. So this would be x to the 1, and this one is technically x to the 0, since there's not an x there. So I don't actually care about the plus 1. This is going to be basically equivalent to taking the limit as x approaches infinity of x over absolute value x. And looking at this piecewise, given by absolute value x over x or the reciprocal, which is equivalent, as x approaches infinity, that would be x is greater than 0, so we would use the first piece. We approach 1, so this should be 1. Now, as we approach negative infinity of the same thing, when we're approaching negative infinity, x's that are less than 0, our result is -1. There is our end behavior. As x approaches positive infinity, y approaches 1. As x approaches negative infinity, y approaches -1. I'm going to begin by drawing the vertical asymptote and any poles or intercepts. Let's go ahead and graph those horizontal asymptotes or end behavior asymptotes. So as we approach positive infinity, y approaches 1. So on the positive side, I'm going to go ahead and put this horizontal asymptote. And then as x approaches negative infinity, y approaches -1. So on the negative side, because it's an end behavior, if you drew it all the way across, that's not incorrect, okay? But I just don't want you to confuse yourself. So the branch to the left of x equals 0 needs to hug this end behavior asymptote, but also needs to hug the vertical asymptote of x equals 0. Knowing that, it's unlikely that this is the look of that graph, but you could always take a limit to check. Just to confirm, I used negative 0.9 and found it to be 1/9. So yes, we are headed in this direction toward positive infinity, which means the option for our other branch has to follow the same behavior on this side of the vertical asymptote, because this is an even vertical asymptote. So we also need to head toward infinity when we approach the vertical asymptote from the right. And then that horizontal asymptote, remember, is our end behavior, so you'll follow that for the rest of the graph. Starting point would just be, I always start with putting those asymptotes and the intercepts out.